All right, hey everyone, let's just dive right in and unlock the visual secrets behind linear equations. Welcome to this explainer, where we're going to take the totally abstract and honestly sometimes confusing world of algebra and turn it into something you can actually see, map out, and touch on a graph. If you're studying the 10th grade curriculum, this is exactly where we build your absolute conceptual mastery, right from the ground up.
So here is our roadmap for today's explainer. We'll start with the two-variable dilemma, learn how to draw our math on a graph, discover the three-line destinies, crack the ratio code, and finally, put it all into practice.
Okay, part 1, the two-variable dilemma.
So, have you ever found yourself totally stuck? Like you've got two complete unknowns and absolutely zero obvious answers? Imagine this scenario. It's straight out of your textbook's first exercise. 10 students in Class X took part in a math quiz. We basically only know two facts here. The total number of students is 10, and the number of girls is 4 more than the number of boys. We have two completely unknown groups, boys and girls. So how in the world do we pinpoint the exact numbers?
Well, think about it like this. A single variable equation, that's basically just a straightforward riddle. There's one correct answer. But a two-variable equation forms a bit of a dilemma. On its own, an equation like boys plus girls equals 10 has literally multiple possibilities. I mean, maybe it's 5 and 5, or I don't know, 2 and 8. To actually solve this, we need a visual map of all these different possibilities. We need a graph.
Moving right along to section 2, drawing math on a graph.
So how exactly do we translate those abstract, kind of confusing algebraic letters into a physical drawing? I want you to imagine taking a magnifying glass right down to a piece of graph paper. To build our line, step by step, we really just pick a totally random value for our first variable. Let's call it x. Then we use our equation to calculate its partner, y. We plot that exact coordinate point on our grid, do it again for another point, and just draw a straight path connecting them. It's literally like leaving footprints.
Let's actually look at the DNA of these lines. Here we've got two tables mapping out exactly how our x and y coordinates pair up. These come from a classic textbook example about buying pants and skirts. For our first equation, y equals 2x minus 2, if we pick x is 2, y becomes 2, if x is 0, y is negative 2. And we just do the exact same process for the second equation, y equals 4x minus 4.
And wow, look at how this brilliantly brings those tables to life. We plot those points on our axes, draw the lines, and look at that. They cross at exactly one magical point, 1, 0. That intersection, that is the exact moment both equations agree. Physically, in the context of our word problem, it means exactly 1 pant and 0 skirts were purchased. The graph literally solved the whole puzzle for us.
Which brings us to section 3. I like to call this the three-line destinies.
You see, when two lines exist on a flat plane, they aren't just random scribbles. They strictly have 3 possible geometric destinies. Think of these destinies kind of like relationships. They can act like two people walking paths that cross exactly once. We call those intersecting lines. Or they can be like parallel train tracks, right? Running side by side forever, but never ever meeting. Finally, they can be coincident lines. That's like someone walking exactly in your previous footsteps, directly on top of each other.
Let's actually give these some proper mathematical names. If our lines meet even just once, like our intersecting lines, we have an answer. The math world calls this a consistent pair of equations. But on the flip side, what if they run parallel forever and never cross? Well, they're never going to give us a shared answer. So we call them an inconsistent pair. There is simply no solution. 0.
And finally, what if they're coincident? You know, riding directly on top of each other? Well, they touch everywhere. They have infinitely many shared moments, or solutions. We call this a dependent pair. And because they do have solutions, they're also classified as consistent.
All right, moving into section 4, cracking the ratio code. Okay, drawing graphs is super satisfying, I know. But what if I told you there's a literal mathematical cheat code to predict these destinies without drawing a single line? Behold the master key. Every linear equation is built using coefficients. Those are the numbers attached to your variables, usually labeled a, b, and your constant c. By simply comparing the ratios of these coefficients between our two equations, like a1 over a2, b1 over b2, and c1 over c2, we can instantly crack the code.
Let's check out the first condition here. If the ratio of those A coefficients does not equal the ratio of the B coefficients, actually scratch that, just stop right there. You don't even need to look at C. It is a mathematical guarantee that your lines will intersect for exactly one unique solution. Boom, they are a consistent pair.
Now, what if A1 over A2 does equal B1 over B2? Well, then we got to look at C. If all three ratios match perfectly, the equations are basically twins in disguise. The lines coincide forever. But if the A and B ratios match, but the C ratio breaks the pattern, they will run perfectly parallel with absolutely no solution. It's incredibly elegant when you think about it. All right, final stretch, Section 5, putting it into practice. We've covered the core concepts, we've got our cheat codes, so let's lock this knowledge in by looking at one final mathematical map. Here is an actual exam example solving a system graphically. We have one line representing x plus 2y equals 6 and another representing x plus y equals 5. By plotting their tables, we can visually see them intersect beautifully at the point 4, 1. X is 4, y is 1. We can even check it mentally, right? 4 plus 2 times 1 equals 6. Yep, 4 plus 1 equals 5. It works perfectly. That is a consistent pair with unique solution.
Now, graphs are absolutely amazing for building that visual intuition. But reading exact decimal points visually on a tiny paper grid, that can be really tough. I mean, what if the true answer was x equals 1.75? You'd be squinting at the paper trying to figure it out. That leaves us to wonder, how can we crack these tricky equations using only pure algebra? Well, that involves the substitution and elimination methods. And honestly, that sounds like the perfect topic for our next explainer. Keep that curiosity alive, and I'll see you then.
All right, let's jump straight into this explainer and unlock what I like to call the ultimate algebraic toolkit for your 10th standard math journey. Welcome in, everyone. Today, we're going to master one of the absolute most powerful fundamental concepts you'll ever come across, solving a pair of linear equations in two variables. And look, we're not just going to memorize a bunch of boring steps today. No way. We're going to build complete conceptual mastery right from the ground up. By the end of this, you'll understand exactly why these methods work, kind of like a master coder suddenly seeing the hidden matrix of the universe. So let's get right into it.
So up until now, you've probably been relying pretty heavily on the graphical method. You plot two lines, and where they cross, boom, there's your solution, right? Easy. But hold on a second. Let me ask you a question. How do you flawlessly graph a coordinate where x equals exactly 49 over 29? I mean, let's acknowledge the struggle here for a second. Guessing where two lines cross on a graph is super easy when the answer is a nice, clean whole number like 2 or 5. But let's be real. The real world rarely gives us pretty whole numbers. When that intersection lands on some messy, microscopic fraction, a pencil and graph paper, they just aren't precise enough, which is exactly why we need a better, more exact method.
But before we roll up our sleeves and start doing all the heavy algebraic lifting, we actually need to know if a solution even exists in the first place. Think of this step as our detective's magnifying glass. We're just going to compare the coefficients. Remember your standard form, right? ax plus by plus c equals 0. Well, by simply comparing those a, b, and c numbers from our two equations, we can literally predict the future of these lines. If the ratio of a1 over a2 is not equal to b1 over b2, we have intersecting lines. That means exactly one unique solution. Now, if all three ratios match up perfectly, the lines are coincident. They're sitting directly on top of each other, giving us infinitely many solutions. And what if the first two match, but that third one doesn't? Parallel lines. No solution at all. This quick little check is a lifesaver because it saves us from doing a ton of unnecessary math.
Okay, so once our ratio check confirms that a unique solution actually does exist, we can confidently push the graph paper off the desk. It is time to bring out our high-precision algebraic gadgets to find those exact coordinates without squinting at tiny grid lines. We're going to look at two primary tools today, and I really want you to think of them as specialized, highly tuned instruments in your mathematical tool belt.
Tool number 1, the substitution method, or as I like to call it, the algebraic shapeshifter.
So here's the core issue. We're dealing with two equations and two unknown variables. Honestly, it's just too much to juggle at once in our heads. Our primary goal is to reduce all that noise down to just one variable. But how? Well, by isolating one variable in the first equation, finding out its shape or what it equals, and then plugging that straight into the second equation. Imagine you're taking a disguised variable, pulling off its mask, and placing its true mathematical identity right into the other equation. Suddenly, magically, you have a simple equation with just one variable. And that's an absolute breeze to solve.
Let's actually whiteboard this together using example 4 from your book to see how it works. We've got two equations, 7x minus 15y equals 2 and x plus 2y equals 3. Step 1, let's pick the easier equation to isolate a variable. That second equation is just screaming to be used because x is almost by itself already. If we just slide that 2y over to the other side, we get x equals 3 minus 2y. Boom! That is our shapeshifter. Step 2, we substitute this expression right into the first equation. So wherever we saw an x in that 7x, we now write 7 times the entire quantity of 3 minus 2y. When we expand that out by distributing the 7, it gives us 21 minus 14y minus the 15y we already had equals 2. Let's combine those y terms. Negative 14y and negative 15y makes negative 29y. So 21 minus 29y equals 2. Now basic algebra kicks in. Move the 21 over to get negative 29y equals negative 19. Divide both sides, the negatives cancel out, and y equals exactly 19 over 29. Finally, plug that back into our shapeshifter equation, and you'll find x equals 49 over 29. Seriously, try finding that precise spot on a hand-drawn graph.
And you know, this brilliantly illustrates exactly why we need this tool. It lets us translate messy, real-world word problems directly into precise math. Take example 5, for instance, the famous AFTAB age puzzle. AFTAB speaks in these crazy riddles, saying, 7 years ago, I was 7 times as old as you were. We can take those confusing English sentences and translate them into pure, clean algebraic equations. Let AFTAB's current age be s and his daughter's be t. 7 years ago becomes the quantity s minus 7 and the quantity t minus 7. We set up our first equation based on his riddle, s minus 7 equals 7 times the quantity t minus 7. We do the exact same thing for his second riddle about 3 years in the future, which gets us s plus 3 is 3 times the quantity t plus 3. Once we simplify those down, we have our neat linear pair, and we can use our shapeshifter substitution to confidently state their exact ages today. No guessing required whatsoever.
All right, moving on to tool number 2, the elimination method. Let's call this one the algebraic eraser. I want you to think of this method like a perfectly balanced scale. Because look, sometimes substituting is just, it's too messy. So instead, we align our two equations vertically, right on top of each other. Our goal here is to make the coefficient, the number sitting in front of the x or the y, exactly the same in both equations. Since equations are basically balanced scales, if you multiply one side by a constant, you absolutely must multiply the other side by that same constant. We gently manipulate the scales until the variables line up perfectly, and then we just add or subtract the entire equations together to make one of the variables completely vanish into thin air.
Let's whiteboard example 9 really quickly to see this eraser in action. We have 2x plus 3y equals 8, and 4x plus 6y equals 7. Notice those x coefficients? We've got a 2 and a 4. If we simply multiply that entire first equation by 2, every single piece scales up. It becomes 4x plus 6y equals 16. Now our x coefficients perfectly match the second equation. We stack them up, ready to subtract the second equation from the first, and basically erase x from existence so we can solve for y. Normally, this reveals our exact y coordinate, but wait a second. As we perform the subtraction on these specific lines, look closely at what happens. 4x minus 4x is 0. 6y minus 6y is, well, it's also 0. And 16 minus 7 is 9. We are left with 0 equals 9.
Which leads us directly into a massive, brilliant trap that the textbook sets up for you. What just happened? Both of our variables vanished entirely. If, during elimination or substitution, your variables completely disappear, please, whatever you do, don't panic. You haven't made a mistake. The algebra is actually speaking to you. If you're left with a true statement, something like 5 equals 5, it means the lines are coincident. They are the same line, so there are infinitely many solutions. But in our example 9 case, we got 0 equals 9. That is a false statement. 0 obviously doesn't equal 9. And mathematically, a false statement means there is simply no solution. These two equations represent completely parallel lines that will never, ever cross paths. So as a master math detective, knowing exactly when to pull out the substitution method versus the elimination method is going to save you massive amounts of time on an exam. It's all about working smart, not just hard. Use substitution, the shapeshifter, when one variable is already sitting by itself, or if it just has a coefficient of 1, like x plus 2y equals 3. I mean, it's practically begging to be isolated. But on the flip side, use elimination, the eraser, when your equations are neatly stacked in standard form and you can easily multiply one equation to make the numbers match up perfectly.
And there you have it. You now possess complete conceptual mastery of the algebraic toolkit. You understand exactly why we balance the scales, why we morph variables, and how to translate the confusing world around you into precise, undeniable mathematical truth. Remember, these aren't just dry textbook steps you're forcing yourself to memorize for some exam. They are powerful, real-world logic tools for decoding the universe itself. So the very next time you face a complex pair of linear equations, just remember, you've got the gadgets. Get out there and start solving.
Welcome to this explainer. Okay, I want you to do something for me right now. Mentally step around to the other side of the desk. Today, you aren't the student sweating it out in the exam hall. No, today you are the veteran evaluator. You've got a red pen in your hand and a massive stack of 100 Karnataka SSLC board exam papers sitting right in front of you. Now, you already know your basic math definitions, right? So today we're going to crack exactly how the Subject Code 81E evaluation scheme actually works for Chapter 3, Pair of Linear Equations in Two Variables. We are strictly looking at high-yield exam patterns and the official key answer requirements. We're going to guarantee you maximize that score. Look, here is the absolute truth, straight from the grading room. We actually want to give you marks. You just have to know exactly where to put them on the paper. Passing the SSLC exam isn't just about knowing the math in your head. It's really about knowing how to display it on that answer sheet exactly the way the official model answer key demands. It's simple. If you make it easy for us to find your steps, we make it easy for you to score. So here is our attack plan. 1. The 1-mark blueprint for ratios. 2. Algebraic step marking secrets. And 3. The 4-mark graph goldmine. Let's jump in. Section 1. The 1-mark blueprint. Focusing on ratios. The board absolutely loves to test your quick recognition skills right at the top of the paper with multiple choice questions. And the ultimate trick for these 1-mark MCQs is surprisingly simple. You see, examiners test your knowledge of linear equations by having you compare the ratios of their coefficients, A1 over A2, B1 over B2, and C1 over C2. You don't need to draw out a whole elaborate graph to know how the lines behave. If you set up these fractions and see that A1 over A2 equals B1 over B2, but definitely does not equal C1 over C2, you instantly know the lines are parallel. They'll never meet. 0 solutions. Boom. You mark your MCQ and you've secured that point in under 30 seconds. And this right here brilliantly illustrates how the board sets traps for you. Just look at question 1, straight from the official 2022 main exam paper. The equations are x plus 2y minus 4 equals 0, and 2x plus 4y minus 12 equals 0. A lot of students try to mentally substitute numbers here. They get totally panicked and they waste time. But look at our ratio check. The coefficients of x give us 1 over 2. The coefficients of y give us 2 over 4, which simply reduces to 1 over 2. But the constants give us negative 4 over negative 12, which is 1 over 3. So, because 1/2 equals 1/2 but does not equal 1/3, the key answer explicitly states the correct choice is parallel lines. Setting up those simple fractions bypasses the examiner's trap entirely without doing any heavy calculation. Moving on to Section 2, Algebraic Step Marking Secrets. Now, you might be wondering, if graphing is so visual and easy to understand, why do examiners constantly make us use substitution and elimination methods for these 2- and 3-mark sections? Well, the textbook actually gives an explicit warning about this. Graphical methods completely fail us when the intersecting coordinates are tricky non-integers. Just imagine trying to precisely read fractions like 13 over 19 or negative 1 over 14 off a tiny graph in a high-pressure exam hall. It's practically impossible. And it's a massive mark trap. Algebra is simply the board's way of testing your absolute precision. So, the absolutely crucial point here is knowing exactly what sequence of steps the evaluator is scanning for when they look at your messy algebraic working. First, we are looking to see if you successfully isolated a variable for substitution or matched the coefficients for elimination. Second, we check if you actually solved for that first variable correctly. And third, we are looking for that back substitution to find the final variable. We are scanning rapidly for these exact 3 phases, so make them obvious. And that brings me to the absolute most important number for your written exam. It's the half mark. I like to call this the half mark hack. If you look at the official evaluation keys, they're literally filled with half marks. Here's the secret. If you make a silly math error at the very end of your calculation, you do not lose all 3 marks. Merely writing down the correct substituted value into an equation guarantees a half mark according to the official key. So listen to me, never ever leave a 3-mark question blank. Even if you just isolate x and literally just write it into the second equation, you have successfully forced the evaluator to give you marks. All right, Section 3, the 4-mark graph goldmine. Chapter 3 contains the single most important question on your entire paper. This is the guaranteed 4-mark graphical method question. Do not skip this. Do not rush this. It is a pure goldmine. Let me just expose the exact grading rubric from the official answer keys right now so you know precisely how to earn every single one of those 4 points. As evaluators, we're instructed to give 1 mark for the first correct coordinate table and 1 mark for the second correct table. Then 1 mark is awarded for correctly plotting those points and drawing the lines on the graph paper. And that final 1 mark, that is strictly reserved for writing the intersecting coordinate values. That's it. That is your blueprint. Let's actually apply this. Look at these 2 tables for the equations x plus 2y equals 8 and x plus y equals 5. By simply calculating that when x is 0, y is 4, and when y is 0, x is 8 for that first table, and doing the exact same simple math for the second table, you have just banked 2 out of the 4 marks. Think about that. You haven't even touched the graph paper yet. Flawless tables are literally half the battle won. Now, once you plot those tables, this is the exact graph the examiners want to see staring back at them. Notice how the 2 lines clearly intersect, and look right there at the point 2, 3. The official evaluation scheme explicitly demands that you identify this intersection. If you draw the most beautiful lines in the world but fail to point out exactly where they cross, you are throwing away that final mark. Let's look at another official example straight from the key answer, this time for the equations 2x plus y equals 8 and x plus y equals 5. Again, the beautifully drawn tables translate seamlessly to the graph. The lines intersect sharply at the point 3, 2, and look at what's right there on the graph. The answer key explicitly notes, from graph, x equals 3, y equals 2. As an evaluator, my eyes are drawn instantly to that final conclusion. But please beware of the fatal mark traps that we evaluators see every single year. First, forgetting to write the scale. You absolutely must write x-axis 1 centimeter equals 1 unit, and the same for the y-axis, right up in the top right corner. Second, missing the actual coordinate labels on the intersecting point itself. And finally, the biggest tragedy of all, failing to explicitly write the final x and y values in a designated box at the bottom of the page. If you leave the intersecting point hidden somewhere in a sea of grid lines and don't proudly declare x equals 3, y equals 2, evaluators are forced by the rubric to deduct a mark. Put a box around it. Make it impossible for us to miss. Okay, so we've seen the traps, we've cracked the algebraic step marking, and we've mapped out exactly how to mine all 4 marks from that graphical question. The evaluator's rubric is literally no longer a secret to you. So here's my question. When you finally open your actual SSLC exam paper, are you just going to be passively solving math, or will you be strategically forcing the evaluator to hand over every single mark? Get out there, take control of the paper, and show them exactly what they want to see.